Here's another example of solving an indefinite integral of type 1, in which the interval on which you're integrating is infinite. This time, our interval goes from minus infinity to infinity, in other words, the real line. The integral from minus infinity to infinity of 1 over 9 plus x squared dx. Now, we don't need to draw a graph of this function in order to understand how to solve this problem, but I think it can be helpful. Remember, our goal here isn't just to be able to solve the problem and spit out a numerical answer. Our goal is to understand what's going on here, why we're doing these kinds of problems, and if possible, to maybe get a sense of what a reasonable answer would be like. So let's at least try and graph this function, just so we can see what we're looking at here. So let's try and graph this function. Now you can use all kinds of techniques from Calc 1 to look at curve sketching and figure out things like the inflection points, the local max and min, etc. of this function. All of those are tools that can be useful to you. I would say in this case, we don't need a perfect graph of this here. We just want a general sense. So what do we know? First of all, this function is symmetric left to right. This function is symmetric across the y-axis because it's an even function. If I plug a negative number into this function, I will get exactly the same result as if I plug a positive number in, because the x is being squared here. So however this function looks on the left is how it looks on the right, in the mirror image. And furthermore, I can plug in 0 into this function, and I'll get 1/9. So let's mark 1/9. Let's say right about here, 1/9. At that point there. Any larger value of x, larger than 0, is going to make the denominator bigger, 9 plus something more than 0. So that means that my y-coordinate is going to be lower. 1 over a bigger number is a lower result. This is going to go down from that point. That point, therefore, has to be a local maximum. You could figure that out using calculus, but you can also just figure it out using logic. And furthermore, as x gets bigger and bigger and bigger, the denominator is also going to get bigger and bigger and bigger, which means 1 over a huge number, that's going to be close to 0, which means that eventually we're going to have to approach the x-axis here. We have an asymptote. In fact, you'll notice most of the functions that you'll see in this section that we're trying to find the area under the curve as on an infinite interval. In order for that area to be finite or to have any chance of being finite, your function had better have the x-axis as an asymptote. Because if it doesn't, the area will certainly be infinite. So this is more or less what our curve looks like. I may not have gotten the exact curve right, maybe the inflection points are a little different, but this is pretty much what it looks like. And this is the area we're trying to find, right in here. The area of this infinite unbounded region. But as we saw in the last example, that area of that infinite region may itself be finite. We won't know until we find out exactly through an integral. The trouble is that whether the area is infinite or finite depends on exactly how quickly that curve approaches the x-axis. So let's actually solve this integral and see what we get. So we're trying to find an integral from minus infinity to infinity. Now, we know from our previous example that if we have one of the bounds in our integral being infinity or minus infinity, that we should change that bound to a variable and then look at a limit as that variable goes to infinity or minus infinity. What do we do when we have both bounds? This is something really important. We're going to need to take two limits here, and we'll actually need to break this up into two separate integrals. So let's first write this here. Let's have the integral from minus infinity to something of 1 over 9 plus x squared dx, plus the integral from something to infinity of 1 over 9 plus x squared dx. Now, this function, we just graphed it. We know it's continuous everywhere, which means you can always break up an integral. You can always take an integral and break up the interval on which it's integrated into several pieces, as long as those pieces sort of match up and have corresponding matching up endpoints. So we could put any number we want to go here, as long as we pick the same number to go as a lower bound here. Let's make it easy on ourselves. Let's call it 0. So let's put 0 here and 0 here. And now we have the integral of the same function across two complementary intervals, the interval from minus infinity to 0 and the interval from 0 to infinity. That together, this union, makes up the entire interval that we want. And now we can treat these as two separate improper integrals. And we'll take two limits here. So this is going to be, let's change our lower bound to a t up to 0 of 1 over 9 plus x squared dx. And take the limit as t goes to minus infinity, plus another integral. Now, I could use t again for that other integral because the t variable doesn't exist outside the limit that I created. So I can actually reuse the same variable twice if I want to. But maybe just to avoid confusion, I'll pick a different variable. Maybe I'll pick u this time. So the integral from 0 to u of 1 over 9 plus x squared dx, and take the limit as u goes to infinity. So our first step was to break up this improper integral into a sum of two improper integrals, each of which has one bound that is infinite. Call that step 0. Then step 1 was to turn those improper integrals into proper integrals in which one of those bounds is a variable, and then take the limit as that variable goes to infinity or minus infinity. Now we can solve these integrals, and each of those will give us a function of t or u, and then we can take the limits. Now, of course, it's the same function in both cases, so the integral solving should be pretty easy. You're going to have the limit as t goes to minus infinity of, see, 1 over 9 plus x squared. Well, 9 plus x squared is a sum of squares. We could use trig substitution here. But actually, we don't really need to even go that far, because we already have in our integral tables the antiderivative of a function of that form. If it was 1 plus x squared on the bottom, you'd know that the antiderivative was going to be the inverse tangent function. And that's still what it is. Tangent inverse, or arctangent. But instead of just inverse tangent of x, it's going to be inverse tangent of x over 3, because 3 squared is 9. And we're going to have a 1/3 in front of that. And that's going from t to 0. Plus a separate limit, the limit as u goes to infinity of, again, 1/3 inverse tangent of x over 3, going from 0 to u. And we'll just work these things out now, and we can fill things in. The limit as t goes to minus infinity of 1/3 inverse tangent of 0 over 3 minus 1/3 inverse tangent of t over 3. Close those parentheses. Plus the limit as u goes to infinity of 1/3 inverse tangent of u over 3 minus 1/3 inverse tangent of 0 over 3. And again, close those parentheses. There's a lot of stuff written here, but don't worry, it all comes very naturally from the prior line here. Just be careful when you write things down that you don't make a mistake and miss some coefficient like I already did. Look at that. I forgot to put the -1 on my tangent over here in this first inverse tangent. So make sure you do that. Okay, now it's just a matter of evaluating these numerical values and these limits. So let's work this out. You do need to take two separate limits, one for each of those bounds going to infinity or minus infinity, because you will get sometimes a slightly different result in each case, and it makes a difference. So let's finish this now. Now I just want to know what's the limit as t goes to minus infinity of this. Well, let's look at what happens. What is the inverse tangent of minus infinity? We can look at a graph of the inverse tangent function. Let's draw it down here. Y equals arctangent or inverse tangent of x. Well, that goes through the origin, and that function goes up like this, and off like this, and down like this. And what is this upper asymptote here? This asymptote occurs at pi over 2, and this lower asymptote occurs at negative pi over 2. If you don't believe me, go back and look at the graph of tangent of x. You will see that that is a flipped version of this where the x and y axes are switched, and it has vertical asymptotes at pi over 2 and at negative pi over 2. So, as t goes to minus infinity, that means t over 3 is also going to minus infinity, and that means that our inverse tangent part here, that is going to negative pi over 2. So actually we have negative 1/3 of negative pi over 2. Now plus the next part. What happens as our u goes to infinity? Well, if u goes to infinity, then u over 3 is still going to infinity. And that means that our inverse tangent of something that goes to infinity, that is going to be positive pi over 2. So we have a plus 1/3 of pi over 2. This is the sum of our two limits, and let's just find that sum. That means we have pi over 6 plus pi over 6, which is pi over 3. And that is our solution. That is the area under that curve, pi over 3. So that integral actually converges because we got a finite number, finite answer. And the area under that curve is pi over 3.